Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Sienny Shang with us today. Hey, Sienny.
Hi, Frank. It's nice to talk to you.
It is nice to see you, even if you're falling into a black hole. It's perfectly great.
Oh, okay. Yeah. So this, but this is not a black hole. This is actually meant to be a young star. That's the thing. That looks always similar.
They have discs, you know.
Yeah, they are similar. Yes.
Oh, that's awesome. That is awesome. Sienny, where are you at?
I'm actually located in Taipei. I'm in the campus of National Taiwan University.
Okay. Are you guys meeting on campus, or are you still working from home, or what's the situation there?
Oh, in Taiwan, you just can work in front office. You probably are supposed to show up at work, and everything's business as usual.
Okay, so you have a mask?
Oh, I do have a mask. We have lots of masks, but this one that you might want.
That is awesome. I love that. That's beautiful. That's beautiful. So here's mine. Mine has northern stars on it.
Well,
so there we go. And we are having a very safe astronomy discussion here.
Yeah, so yeah, that's what Taiwan is about. Let's say, so we have lots of different masks, and people are required to wear a mask everywhere. So classes are back. Conferences are back, but just like in those crowded space, subways, essential business, you're required to wear a mask. But people are just taking it as a habit. So no matter where we go, we just wear a mask. We have other kinds. So this is a Chinese New Year.
Oh, fantastic.
So this is the New Year of Ox. So that's what the Chinese New Year mask about.
Beautiful. I love that. I love the colors of that red and white, red and gold. Very pretty. Love it. Love it. So are you teaching right now that if everybody's back in?
Actually, we are not teaching in our institute, so we are a research institution. So most of the time we do research and a lot of other work. We have lots of projects in our institute, so we do different things. But yeah, so we are not teaching is not required.
Okay, so cool. Speaking of research, what do you like to do for research?
I'm actually doing research on how young solar system forms.
Okay.
And so we do things starting the physical process of how we start from a cloud, so a molecular cloud, to form a young star, and we can form jets and outflows, and we form a disk, and or vice versa. So that's kind of research overall I'm doing. I'm studying the theory of it, or we use simulations. Sure. And yeah, sometimes I participate in observations.
Yeah. Ooh, cool. Double threat.
Yes, but that's fun. That's fun.
Oh, very good. And that is going to lead us to this very lovely APJ article on a unified model for bipolar outflows from young stars, the interplay of magnetized wide angle lens and isothermal toroids. And Sienna, take us away.
Yeah, so this is one of our latest updates on theory on studies along this area. So we are trying to form molecular outflows. We're trying to see how molecular outflows could form with different interaction from a wind, or either from a wind, from a jet, or what's the ambient medium. So in this part of the theory, we are actually we were able to integrate a wind with a strong jet component in a similar way that you see in my background. There's a strong jet in the center. There's a wind going back, going out, but you don't see it because it's the density is lower. But nonetheless, it carries a lot of momentum. And then what the ambient medium is about, and we have ambient that's coming from as isothermal toroids, which is a part of evolution from process the equivalent evolution of molecular cloud to form cores. So this new paper is about the magnetized interaction. So the wind is magnetized, ambient medium is magnetized. So when they interact, there are many interesting things happening that we didn't know about. So they can form a bubble-like structure, and the bubble has many layers of structure inside, and then they have they are shaped by magnetic field outside. Between the outflow and ambient material, they are strong shear, and we see lots of interesting phenomenon of Kelvin sensibility, and that generates all the fascinating internal structures to molecular outflows that we didn't think about before. So that's this paper about.
Very nice.
So and so we gave an introduction to the paper and pretty much went through the we gave a little bit of historical account why kind of specific wind model or with a strong jet component is important. That's because there used to be a consideration whether from observational point of view, whether a molecular outflow is driven by a jet or molecular outflow is driven by a wind. Because some molecular outflows are very jet-like, you see strong knots in the center, and some outflows are really wide angle, and you see only pretty much left with oblique cavities around the central star. So then that has been a so-called jet-driven paradigm or wind-driven paradigm. And people have been over the past 34 years, there are many different scenarios about what molecular outflow is about, and whether it's there's an underlying stellar wind or there's just a jet shooting out. And then so there are many different arguments, cavities and opening angles, whether the jet is wandering. So that we went into a little bit of theoretical, historical account of it. And then so then we went to discuss a specific kind of the model, and so-called X-wind model, where we consider a strong jet component in the center that's naturally coming out from magnetic collimation. And so for that matter, so the magnetic collimation will give us a very strong cylinder density stratification. So that actually looks like a jet, just like my background image. And whereas the wind is is launched at wide angle, meaning it's really giving the momentum push to get the kind of opening the shape and the like. So at least it carries significant amount of momentum in the angle that's away from the jet. So despite the fact that there's a jet, so there's this angle component that's a wind model, X-wind model that's proposed originally for Toroid star, but then it's can work with the protostars by its theoretical development. So for that kind of model, for this matter, so we use this kind of wind to interact with ambient medium that has also its own density structure, which is part of evolution of a magnetized collapse, part of a magnetized collapse models. But although in this paper we didn't really collapse the cloud anyway, so we just adopt the density structure and magnetic field structure, but we still came up with a very complex interplay.
Yeah.
So
don't you let that roll?
Yeah, so for different, yeah, so you were, yeah, so for this part of the introduction, we were actually, okay, so I kind of went a little bit too fast. So this part of introduction, I went into the observational support of um, models and different kind of suggestions from the discovery of class zero sources. So in class zero sources, I think that's on the left part of the page. In the class zero sources, we've been studying with some awesome jet sources called HH211, HH212, IRA 04166, and there's another source L1448. The peculiar part about the sources that their appearance are very elongated. So that means they are so elongated and then people just thought it's a jet-driven model.
Yeah.
But on the other hand, with a new advancement in submillimeter arrays, so from the study of submillimeter arrays, we've been following those jet sources, and we would be tracking to detect their velocity structure and their with different tracers such as SIO and CO. And in that manner, then we were able to pin down the launch region of those sources. They can came from 0.05 AU or smaller. So such the case for H211, H212, they have a jet that's coming from very small region. Yet, in the past study, the traces of those jet sources that have a velocity, when one study its velocity structure near the base, they do show the wide angle kind of feature. So the velocity width is very wide if one go down to the base of jets. So that means those early sources may be good candidates of or models that could carry strong jet and wind components together. And when they are young, they must be deeply embedded in their native cloud cores. So, interaction of this kind of wind jet model with a surrounding cloud cores native in a very its early form, then that will give us very interesting ideas. So yeah, so we also have a way that to mimic the transition. So we'll go through it in later in the part paper. And one part I mentioned in the last part of introduction is we have done this kind of series. People have tried to detect the magnetic field in the cloud cores, and then also in the jet. So in the case of H211, there was a hint of magnetic field structure, helical magnetic field structure lined up along the H211 source. So that's a good support for things we're going to talk about. And then that gives a very strong hint that the jet collimation may be supported by fields that have a very strong toroidal component. And the part theory model we actually putting into. That's about the main observational support. And the rest about the introduction is previous attempt from my group about early last attempt that we try non-magnetized model and using computer resources at that time. So we were able to do a precursor of the things we were talking about today and using Zooscope, but different coordinate system. So this paper, we use a different coordinate system, and that's the way it is. And so that's going to talk about in methodology.
Thank you.
So, okay, so methodology. I skipped a little bit about the intro, but then that's I think we'll put it back in the later part. So methodology part, we went through a little bit of derivation about why we use the wind model as it is. We were demonstrating why we went through this derivation. Now it's because we were trying to show everybody, at least in its mathematical form, that the a solution that bears with a strong cylindrical stratification and a radial component outside the radial velocity is a generic solution, but it's in the co-limit. So as long as our sources are cold enough, and then it's cold and it's non-rotating. But well, people may argue, well, it's not rotating. But then in this, in its a simplified form, we will demonstrate when we make assumption that it's non-rotating and as its symmetry. And so we can show that this special solution is, as we adopted, is just coming out from the whole set of equations. So there's no magic about it.
Yep.
And so this is part of MHD property of such a wind. And this helps a lot in simulation of this sort, because then we can study the interactions as some places slightly far away from the launch region. And so this launch region is considered to be small, and that's why this assumption can be made. So we use okay, I guess I need to go back a little bit equation, looking at what's on this page. So I'm going through a little bit too fast.
That's okay. What equation you want to reference?
Actually, I'm just going back to this page. Yeah, because you were at this page, and this page, I just zoomed through about the simplification in magnetic force, simplification in induction equations, and so we do it in the general way from Maxwell equations for both the wind and for both the ambient. So in section 2.1, we just did it in a generic way. We didn't differentiate whether it's wind or it's ambient medium.
Right.
And we show that in spherical coordinate system, they can be reduced somewhat, making the axisymmetric assumption and non-rotation assumption.
Yeah.
Then in equation 15, we have included this component of vorticity, which we'll later use in this work, because we actually studying a region which which will generate a lot of vorticity. And in that sense, we also spell out the spherical components. In spherical coordinate system, the vorticity, how we express vorticity. But in this work, because of all the symmetry, we assume we only will look at the phi component of the vorticity in this work. So since we are deriving everything together, so we outline all the necessary quantity in spherical coordinate system and laying them out, so making necessary assumption to the point before they are further simplified. So in 2.2, we focus on the magnetized wind. So the magnetized wind, we actually make further assumptions. And that means we assume there's no Poloidal component of the wind, in addition to non-rotating assumption. Mm-hmm. So in that case, we can further simplify the equation down to equation 16. and 17 for the force component.
Yes.
And yeah, and then we further reduce the induction equation into equation 18, so we can safely keep the phi component of the magnetic field, and both components. So far, we still keep both components of the velocity Vr and V theta.
Yeah.
Yeah, so there between 19 and let's see, so that's up to equation 18. Then we go down to equation 19, 20, 21, 22, 23. We kind of discover a way to, when we look at equations, once it's simplified to this point, we found that we can actually further rewrite the current in cylindrical coordinate system, that we can define a writing out equation using cylindrical coordinate system for a little bit in 19, but then we can rewrite, because then we can calculate the component much better, much clearly in equation 20. So in the equation 20, we can see that we can define that the toroidal current with the axisymmetry, we can write them express them into a form that we lay out in 20 as a gradient of C, and then with taking a curl with phi direction. So which means this toroidal current can be expressed as quantity related to C. Then what is C? And C we name, because of this connection, we name C of a current function. Okay, so it's related to curly pi times B phi. So this means that it's actually giving us a very good, a lot of insight into how we calculate the B phi, or use B phi to calculate C. So how we connect current in this format, and the phi component and magnetic field. And in equation 21, then we further go down to calculate the force. Then when we calculate the force using the B phi, and in this expression of current, we realize we can further write down this force as a gradient of C squared over 2. And then, well, we do have this 1 over curly pi in front. But this gives us an idea that if we define as equation 22 as C squared over 2 as a force function, so we actually can write down in the simplified form of force in equation 223. Kind of gradient of this force function. So this is an interesting concept that we'll later use, that we found a very informative when we were trying to understand what's happening in the system. So taking this detour, okay, this is a little bit detour, but we feel that conceptually it has to go in, because of the expression of connection between the current and C function and the force function with B phi dominate system. We actually go back to the simplified equation, and in equation 24 and 27. Actually, yeah, we can write these 4 equations without the detour of a C function, and force function, but that's just cool. We'll see later. And then, so then 24 to 27, we can demonstrate that there is a solution as complete radial velocity, and then density rho curly pi squared, and B phi times B5 times curly pi, as we show in the parentheses between the set of equation 24 to 27. These three things are natural solutions for this simplified set equations.
Nice.
And so I mentioned a few minutes before that we thought theta is very small, and then we are as we see actually in our simulations later on too, that the radial component, even though there's a v theta usually is small. But so that means this equation kind of holds well, holds pretty well in a good bulk of simulation domain. And so this, I think, so far as far we know, this was the first time this equation could derive in the spherical coordinate system, and writing down in this kind of form. Other than the previous two works, Li and Xu, 1996, they just mentioned a cylindrical coordinate system. And the other connection we made here is to the X-Wind model and asymptotics. Yep. So in that there were similar analogy about deriving a simple asymptotics for X-Wind solutions in the spherical coordinate system. And there was a function C defined, and then B5 is proportional to this Cx over curly pi. And other than sign differences, we guess slightly different in sign, but they could be analogous to each other, although the X-Wind model has a different launch origin. So with velocity, terminal velocity going through as in equation 29, going through there's a different expression. But equation 28 is literally what we had derived about. Well, I guess you don't want to go back and forth, but there was a similar equation we derived earlier, but then it's pretty much the simplified force balance equation and across the string line. So we show there are some similarities, but there are differences because of the way we formulate equations. So then we identify possible regimes that could be similar to the X-Wind model, because X-Wind model does have this feature of a strong cylindrified density contour, and also a wide angle wind. But wide angle wind part can be angle dependent too in velocity. So here in this formulation, we slightly simplify further that we can demonstrate this a purely radial wind. That means we can give a constant velocity in all directions. So then we make analogy of the regime. They might be relevant. Because of different formulation, we kind of try to, there are differences how we compare them. So in this work, we will, in our later sections, we kind of parameterize using a parameter alpha Mach number. So we did, that's the definition is a Vx over Va. We just use the X notation for X when this work. Okay. But in that concept, they are similar. But the regime of validity, the alpha Mach number, and our parameterization is slightly different because in our current work, we can directly use alpha Mach number as a parameter. There, in the asymptotic X1, the things will change along the string line. So that approximately connects to asymptotics. If we were talking about X1 model, then that will be in the mid kind of region outside the wind effort is making the super fast transition. Okay. And then, or going down to large distance.
Yep, I'm with you.
Okay, so 2.4, we kind of just recap a little bit about what this theory is about singular isothermal toroids. and we calculate, we also write down the equation. But contrary to what we did for the wind, we assume there's no toroidal magnetic field in the toroid,
Right, purely.
and therefore it's purely poloidal.
Yeah.
And in that, we can also simplify the equations, and then we can derive equation 33. And equation 33, we can show that the density profile and its magnetic flux function is purely separable. So there's a port that's dependent on radius, it's a port that's dependent on theta. And phi function is the same, it's separate. It can be done by separation variables and an R function in front and theta function in front.
Mhm.
So there we took the solution from the paper of Li and Shu, 1996, where we can solve the different configuration toroids in a parameter called H0. And H0 we use n because we like it to be integer. So integer is more convenient when we label the different configuration. So that will be used as our initial condition for the setup. And so 2.5 is to bring in the concept of forming molecular outflows using conservation of momentum. So this concept came from we call SRLL, is Shu, Rudin, Lada, and Lozano,
Yes.
1990. And they actually formulate the question about what parameterize the equation of density distribution of ambient medium using some form similar to single isothermal sphere. Single isothermal sphere. So in a way that the parameters can be separated. Just like right now we use a Q, although you see equation 33 and there's a R function. So then on the other hand, contrary to other parameterization, I guess in different field, the injection of energy, injection of momentum can be formulated differently. But there, in the concept from SRLL was that one can parameterize the momentum coming from a wind, strong angle, perhaps angle-dependent wind, by just parameterization of wind up, V up over 4 pi. And then there's the angle dependent function.
Mm-hmm. Mm-hmm.
So, and then the wind just sweep into this ambient medium, and we can sweep up a thin shell.
Right.
And there, so there was some assumption made too, but we can basically write down equation 37 and 38 using the conservation mass and conservation momentum, pretty much in that change of momentum, change of mass is how things are with how the ambient material is split up, and the change of momentum is purely given by the injection of wind. So by this equation, this setup in one can derive in equation 39 and 34, 39 and 40. Beautiful description of the shell. Yeah, and then later on, and we can see whether the wind with a strong cylindrified profile. So which is with a strong jet profile, if we give a momentum, giving a strong jet momentum, whether that gives the right shape. So that's pretty much a hydrodynamic momentum conserving thin shell model and momentum in function. So it looks like simple. We just put in P and Q and we get a shell. So there was, of course, there will be a little bit different consideration. Suppose because the wind has its own mass. So what if the wind accumulates mass? So then that's what's written in equation 41. So, and then we can rewrite the wind pressure form in equation 42. And then we compare with another formulation done in Kuemaki. So we can actually, they both use the same simplification that the velocity is roughly changed a little by accumulating mass. So there we can get a different format of equation 44, where the shell velocity can be given as a density ratio. But then the two formulations up to this point are similar. So that's the background for this before we got the conclusion of this, the rest of the work. So that's where things were when that went into the model.
Okay.
So that's section 2. So, okay, in section 3, we set up our simulation. So simulation wise, what's special this time is we didn't use, we kind of use isothermal model, but in order to consider the difference in the wind, in temperature in the wind, and the cold ambient medium, we actually have devised a 2 temperature setup, where the sound speed is given, or the sound speed is given by for equation the 45, such that we introduce f function, which is a mass fraction of the wind, where the sound speed is given by interpolation of the wind material and ambient material. But within the wind cell, it's 1 temperature, and outside the toroid is 1 temperature. So it's a 2 temperature scale. And there, we have there we do, the rest of this subsection, we describe how we set up a grid, where we set an inner radius about 1.5 AU. We have a very large outer radius, 10 to the 5 AU. So we have quite big computational domain, and we use an uneven grid. So we can design grids so they can cover the right range of right range, but we would grid allocated in locations we like to be more resolved than the rest.
Okay.
So this one is 3,200 cells in the R direction and 1,008 in the theta direction, and there's a different step that's double the size.
Right.
Okay. So,
good. I'm with you.
So let's see. I need to make sure I'm following my own text. So
yes.
So yeah, okay. So in the wind region, so then what's the difference between how we use those 2 temperature setup? So in the wind region, F is 1 because it's purely wind, and so therefore and V5 is 0 and BP is 0. And in the outer part, and then that's we do, as we said, B5 is 0, but BP is present. But we'll see that we actually formulate a different BP, so we can study the impact of different strength. So and then we do have one set of solutions that means there's no toroid. So that means the wind just zooms right out, and it's freely expanding into the fill of the domain. So so here we clarify, because we didn't study the clock's problem, so we didn't allow the cloud to follow gravitational collapse, although that's a desirable goal. Okay, so but in this paper, just for this work itself, we didn't turn on the self-gravity, so it's not collapsing at least. So we're studying the propagation.
Understood. Okay.
And for boundary conditions, 3.1. So yeah, so all the set simplification, duration, demonstrating the wind has in the property of wind. We set them up as a boundary condition, as shown in 46, equation 46. We adopt a parameterization of the density going through d0 over Cali pi squared, because we show the density has to follow 1 over Cali pi squared. And b pi follows 1 over Cali pi, and we give it constant v0 to begin with at the inner ejection point. And we have v0 as a purely radial wind to start with. So v0, and since it's it's radial, it's v theta is 0, and it's purely radial. And yeah, so the wind farr is set up as a boundary condition. Then we talk about this auxiliary field that we implement into Zeus to solve to make the requirement.
Quadrant. Okay.
Then 47. Okay, so down next paragraph, in equation 47, that's where we talk about the Alfvén Mach number. So previously, this is slightly different parameterization between this work and what the other work adopted for actual models. In that because of MA, the Alfvén Mach number, and this completely radial wind and strictly cylindrically stratified density profile, we can write down the Alfvén Mach number as our initial parameters, shown in 47. So we adopt Alfvén Mach number as our one way to express our parameters as a combination of V0, D0, and B0. So we can get them one way from the other. And BMA is so we use MA numbers to label our sequence wind magnetization.
Yeah. Okay. All right.
Okay, let's see. So we fix MA, once density, radial velocity are fixed. Yeah, that gives the scale and value for the toroidal magnetic field in the wind. Yes, that's how we do it. And so let's go to the right column. If you don't mind, if you can give me the top of it. So yeah, 3.2 is the initial condition. So basically, initial condition deals with how we set a toroid. So the toroid part, the ambient part, is actually set up as initial condition. Contrary to the wind part, set up a boundary. It's set up an inner boundary. And so the initial condition of the toroid is given in 48 and 49 and 50. So we actually, in equation 48, we actually adopt a mild density floor. So in the format of 1 over R square.
Right. It's your spherical
profile. So one can consider as a purely spherical isothermal sphere in the background. We give a small value of ds. It doesn't change the mass much, but in that it's tiny. It's stabilized the simulation. Okay, so it serves dual purpose. So it actually helps so making all the simulation stabilized. That can run for a long time.
Good.
And so equation 49 and 40 are just the details of how just add them up. Okay, and the simple added up. Then we describe, and in a small paragraph below, we describe what's the temperature difference in terms of sound speed. We chose a sound speed 0.2 kilometer per second for the ambient and 0.6 kilometer per second for the wind. Well, but converted, I like to, well, it's about 10 Kelvin. That's what people use all the time, but it's actually 1124, 11.24 Kelvin. And the other one is 101.2. It's a, yeah, round off. We call it 10K and 100K.
Yeah, it's roughly a factor of 10.
Yeah, yeah. So physically, why we chose this? Well, yeah, strictly speaking, we can have many ways to do the cooling or many ways to calculate temperature. But for simplicity, keeping it as isothermal is not too bad in that people have been studying those line ratio studies and from LVG method, well, pretty much by fitting available observational data, one could get about the wind, well, bulk of the region. Of course, there are some small region that may be hot, but bulk region on average, they could be treated as 100 Kelvin wind, and toroid part, or one usually people consider molecular clock core circle 10K. So that's it's a kind of self-consistent observation confirmation about the choices of parameters. Okay.
Observation inspired. Okay. Parameter space.
Yeah, parameter space. Wow. Okay. So this part makes myself dizzy too. So okay.
When do we get to it?
Yes, I need to count myself how we did it. So Mach number, we actually cover, so things can be done. Well, yeah, we summarize everything in table 1, and hopefully I don't need to count. So we have table 1 for MA, the Mach number. Why we chose the way it is because, well, 6 happened to be historical reason. Our early work, we adopted 6 for strong wind, strong magnification. And 600 was one we chose maybe weak enough. We can show it's almost non-magnetized. But now in this work, we actually include a set with that's purely hydro, that's infinity. So it's alpha Mach number being infinite. So the numbers in between 36, 90, 180 was chosen because we want to see how things are changing if we change magnetic field strength in a way that kind of giving some information and different strength.
In a controlled manner. Yep.
Yeah, and it turns out to be very informative. And V0 and V0, we use 2 different velocities, one is 50 kilometers per second and the other one is 100 kilometers per second. So for the information, because observationally, the molecular jets that people have infer from observations or proper motions that the jets can be moving between from 50 kilometers per second to perhaps 2-3 times a bit. So maybe 50 kilometers per second to about 150 kilometers per second. So we chose to study by a factor 2, 50 kilometers per second, 100 kilometers per second.
Okay.
And the choice of the ambient temperature we mentioned already. And here we used 4 different kinds of toroids from N value 1, 2, 4, 6. For simplicity, it's easy to remember 1, 2, and 4, 6. And we'll see later why 1, 2, 1, 4, 6 is because they show us to give us a different feeling about what the result of what the environments are. So 1, 2 will give us environment that give it relative early. 4, 6 somehow already can tell us a lot with a kind of wide open environment. So we'll see the result. Then there we use the 3 different kind of parameterization for ambient field strength. Well, the solution itself should be 1. But then we want to study what if we change the field, but we keep the density. So we study the 3 alpha B. So 1, 0.1, and 0.
Okay.
So yeah, so that's a huge parameter space. I need to count myself what we are doing. So equation 51 is just for the plasma beta. So just so we can also calculate plasma beta to see which region we are roughly in.
It's a lot of models.
Yeah, for those models. Yeah. So we can see the corresponding plasma beta in the table 1, 2. Okay, so I guess we finished the setup. So we set up alpha, we set up different parameters. So we have 2 parameters of velocity, we have 2 resolution and stuff like that. So that amounts to 168 cases or something like, 168 cases. That's huge. I fail to count sometimes. Okay, so numerical results. Then section 4, we talked about numerical results. So we lay out we contrast, we can compare and contrast. We set up the background, the basic flow structure. We illustrate the property of the wind and flows, and we just study the interaction and see what this new interaction tells us. So the first figure 1 and figure 2 are actually some for the same purpose, figure 1 and figure 2. So figure 1 is the wind with 50 kilometers per second, and figure 2 is the model with a wind of 100 kilometers per second. So actually, I prefer to see, let's show figure 2. Because 2 is slightly even more clear than figure 1, because the solution. So this page is kind of used as giving everyone and ourselves too what's the background flow is like. Why I like this flow better is 100 kilometers per second. Even gives an even better approximation for the solution itself. So it's when we solve it for full equation, it's even better than 50 kilometers per second. So this kind of is a self-consistent check how good our approximate solution is, because we set up the when launched as a small region and we let it go, but the equation in the code is full equation. So it's so figure 1 and figure 2 are kind of doing a self-consistent check, and so they seem to be doing very well. 100 kilometers per second wind seems to be better than 50 kilometers per second wind. So, but then they didn't fail us. They are doing the job as they do.
Okay.
So so both figures are having 2 panels. The top panels are for the density structure on the left, shown in yellow, but magnetic field structure to the right is shown in gray. So both of them are meant to show that they are cylindrically stratified. So we show on the right panel, the right part of the top panel, the grayish part is negative pressure. So it's giving the same 30 pi dependence as a density. So we are showing that they pretty much are doing well, corresponding to each other left and right.
Got it.
Then okay, so
I'm with you.
Okay, so for the middle panel, we are demonstrating the time. So one is done at 100,000 years, the other one is at 5,000 years. So that we are showing that we are reaching steady state. They pretty much not changing at all.
Right.
And then on the top, we show the full scale, because of the full scale and much bigger physical scale. So we are showing that this kind of cylindrification, this kind of structure can go on for a long time. Okay, can go for over long, huge physical scale.
Okay, good.
And so then the bottom one is a PV diagram. PV diagram, meaning that we are trying to show that in terms of this, how people infer the structure for the wind, and PV diagram can tell us how the velocity spread changes with the distance along the jet. So here, in reality, people can get many different kind of inclinations, but here, just for simplicity, we use an adjunct system. We view the system 90 degree, so we can see that how we translate the wind structure that's that cylindrically stratified like this can translate in a column density structure like
okay. So the color bar on the last one is column density.
The color bar for this one is column density. Oh, sorry, I just realized I can move around the cursor. I didn't. I thought I didn't. Okay, so thank you. Now I can move around. So yeah, so here this is yeah. So this the color bar here is a column density.
Yeah, yeah.
Okay. Color bar, and here is the velocity spread is how wide the velocity is captured going around different directions.
Mm-hmm.
So what's special about this kind of structure is, despite the jet, so we will get a visual impression that it's actually a jet. But so the position velocity diagram can tell us that it still has residual velocity going to different directions. So basically, we can see the rate, the components are going toward the observer. So there's still a residual width. So that gives the foundation that there's the width is there, despite the, even going on for a fairly high distance. There's still, it's not zero. So it's not zero if we were to expect from a vertical jet.
Yes.
So that's the point of those plots.
Thinner and thinner. Okay. Mm-hmm.
Yeah. So let's go down.
Axis. Okay, I'm with you. Mm-hmm.
Or can I move around, or this? Oh, you can move around. Thank you. Yeah. So let's go to next figure. I guess figure may be good enough. So figure 3 and figure 4, by the same token, they are the they are the structure of the results from 50 kilometers per second wind and 100 kilometers per second wind. So figure 3 and figure 4, we set up the toroid. We have toroid in the background here, and we show them in 3 panels. So this first panel is the full strength of ambient polydal field. The middle panel is a factor 10 smaller. The right panel is of ambient medium that's not magnetized.
Yes.
So and then the wind. So the wind is shown, and okay. So the ambient, so the toroid is shown in 4 numbers. Then we label on top and equal to 1, 2, 4, 6, 1, 2, 4, 6.
Okay. Then it is the different.
So then the Mach number here, alpha Mach number here is labeled from top to bottom.
Okay.
Here. So from 6 to infinity.
Okay.
From top to bottom.
Okay. And the contours?
The contours is labeled as actually as number density.
Okay.
So it's shown in the mirror plane, the number density of the distribution.
Got it.
So then there's in the light white lines or the magnetic field structure around the form molecular outflow lobe. So it looks like lobe. Well, it's just same terminology from observation is a lobe there. So we see the appearance change. Well, they are the same wind as you see in figure 1 and figure 2.
Yeah. Mm-hmm.
So yeah, so we can go. So this is figure one. So this is the same window figure one.
Yeah.
And if we, Frank, if we can go to figure four,
Yep.
so that's to figure four
Yep.
slightly because the same. It's not that both are showing actually slightly different feature, but figure kilometer per second when the features seem to be more um, pronounced.
Yeah.
So
Yeah.
so you see it's more elongated.
Yeah. Skinnier needles.
Yeah, it's skinnier for smaller end, and because you see obvious, you can see that from smaller opening angle, not
Yeah.
small,
Sounds.
small, small crack in the middle, then it's coming out from the very small, and a small density, low density region. But then on the contrary, for large n values, you can see we see the form outflow shape is much wider. And between from here to here, from n small n to large n, we see the change of shape from very elongated, very columnar molecular outflow structure to the more traditional wide angle molecular cavity. That usually indicative of a more evolved status. So here we can just so we can see it changes by it changes the appearance completely by going. So usually people one would refer molecular jets. Those may be called molecular jets. Those may usually be considered as wide angle, the wide angle molecular outflow cavities. So they usually, so this is a good time to talk about some of the what I mentioned in the introduction. I didn't really go into a little more detail. So these are usually considered as coming from slightly more evolved late class 0 sources or class 1 sources. Some in terminology of young star early evolution. So that's why here we can capture all the different shapes roughly. Of course, if we can extend the Toroid solution going on, well, we definitely can get a little more. But I guess this is illustrated enough that we can know the change. We can see the variation of change. And then we see here is so we see the shell. We see the formation of shell structure.
It's certain MAs, right? You're talking about these pileups, right? Yep.
Yeah, they have pileups right here, right here, right here, and then
sort of intermediate MA. You get these I don't want to say they're periodic, but you get these pileups at specific radii. Whereas you go to very high Mach number, everything looks smooth and no pileups, and the same with very low Mach number. It's a smoother flow.
Right. But then when one notice, so roughly we give a kind of we can go from the highest highly magnetized situation going down this way. So you see that, and they change. So this is then you see the stuff that's pileup would also pileup would feel too. So pileup here and here near the base. But one can observe some differences from going of a trend going down this way. So one can see that there are differences in this highly magnetized cases. They really appear as needles, and roughly they are really clean by appearance, but then we'll see later it's not complete clean. So it's a very collimated jet, as we show in the solution so well. It's holding up as well as it can be. But in the middle range of Mach number, you see variety of structure that's changing from cases to cases. But I think we turn to the piece. we seem to be returning to some peaceful situation. And the non-magnetized wing port,
Yeah.
that they are going back to kind of clean surroundings around the jet. So,
Mhm.
but the jet, we can see the jet kind of diverging a little bit, so they appear wider on top. So those are, that's magnetized. They are now, this is not magnetized, it's hydro wind. But here you see it's remaining as a cylindrical stratified as it can be going out there. And so we'll talk about, and then we'll talk about the structures. So we see structures form around those jets.
Uh-huh. Mhm.
So, and that's just give the glance of what the morphology is for the cells.
Very nice. That's outflow blows. Then we have some tables.
Yeah, so here we talk about, well, this is kind of for observers. They would like to ask what kind of cavity it is. That's the tables.
Yep.
We actually try to fit the cavity, and also for all the cases, we calculate the aspect ratios. So that's for lookup reference.
Yes.
True.
And opening angle for different in these properties of the shell bits. Yep.
Yeah, so we also try to, there, we'll see there we have shell fits, so we kind of give that numbers too. So here is actually some figure 5 is what I just mentioned. And so figure 5 is actually a recap of the previous figures, but we actually this is what's special is to show that we have 3 different ambient environments, but the wind here are the winds are all non-magnetized. They are hydro winds. So this is to emphasize the fact that the structures we saw around the jet were only present when the winds are at least moderately magnetized.
Yep.
So in hydro wind, we don't observe that situation, although we see something slightly different. But then overall we have thin shells surrounding it. Doesn't matter. It's a magnetized ambient. Although the ambient seems to be slightly different, that we see there a bigger opening, a gap between the outlining shell portion and outer part. So we show that so they form 2 layers of cavity where the cavities here are kind of mixed together. So the same things are happening here too, but it's just more obvious to see when the outflows are sticking out of a more wide open background.
Okay.
So this summarizes a lot of details about what we wrote about in section up to section 3. I think we can, we kind of finished section 4.3 in the figures. So we can do section 4.4. So what's about section 4.4 is summarized in figure 6. Here we starting from figures 5, we actually use one of the 100 kilometer per second case as just to demonstrate the points. Although qualitatively the points are similar. The characteristics are similar for 50 kilometer per second winds. Here, so what we found out for the study is that the molecular outflows is no longer a thin shell in most magnetics in most cases. Instead, they come into many different layers. There's actually a loosely defined language, so that we can, but because that's by visual impression, that's what it looks like. Theoretically, they actually came as a different theoretical structure. So on this scale, this is shown at 3,000, I think vertically 3,000 AU scale. So and on the horizontal scale is shown on 1,000 AU scale. So we see a change. So if we do a cut and we see the changes in the detailed structure, kind of traditionally the shell portion of the molecular outflows. So okay, so let me talk about the intuitive the appearance first, and then we talk about the theoretical structure. So the appearance goes like then, so the jet part is actually aligned in this 0 point. So you actually, it's really hard to see, but here, because this part, the jet in the hydrojet, you actually can get a jet better. So they are fair, so you see. So, but here you can see a little shade. So right here. And here is, and then the red part is the density part, the toroid, that's deep into the close to the midplane. Then here we see the variation, not only the shaded part, the density, the color part shows the density contrast, the density variation. But we see that in all those cases, okay, first of all, we talk about, we show the comparison between the magnetized ambient and non-magnetized with medium. So we see this is a scale we show that the field actually goes in between the internal part of the molecular outflow and outer exterior part of the outflow. So here is the historical part, the traditional part of the ambient part, even though strictly they do have a little stuff here, but we see the separation of material of shell structures between an inner shell and outer part. And here it's less dramatic, but it's there. So it's there, but it's really hard to see. But this is most dramatic in the most open toroid. So we see the separation and feel that there's a bar. This bar is so it's dark. It's just because the matter density is lower, but not right in the field. So, but then we see that interior to this field surrounded portion, we see development of structures.
Yeah. Okay.
Right here in all those cases, although detailed structures are different from one case to the other. And we see at least at this scale. So we'll talk about different scales and they show different scale structure. At this scale, the 3000 AU, that this for the magnetized, strongly magnetized wind, they seem to be more structure that something like this going into the jet portion. But in the middle part, they seem to be developing more swirly structures around.
Yep.
And yeah, the same thing repeat. The only difference is that for the weakly magnetized case, we see still because the magnetic pressure is much lower, we see there is a very small portion of those, but just because it just go all the way, the wind just ground pressures go all the way out. So this portion is much smaller. They appear to be connected, but actually they are not. So you see the change of shape because this one is they are really connected together, and you see their structures much different. Although interior to it, they seem to be developing the same patterns.
Yep.
Okay, so okay, so that's what we meant in this in terminology in section 4.4 as multi-cavities and multi-arcs. So what is multi-arc? So let me defer other definition. Let me just talk about multi-arcs, meaning we see structures actually going also in between, develop in between here. And so that won't be present in the here, we probably won't be able to see it, but it's not here. So it's in between the shell confined by a field interior to the outflow and between the outermost ambient toroid. So there are some kind of arc-like structure going outwards. So on this scale, it's down to 1,000 AU scale. We see more clearly the division between a wind portion, and we see that using the F value, okay, as an indicator about the rough proportion of the wind material. So we see a transition between the wind material by the dotted line.
Yep. Yep, that was true on the other one as well. Dotted line.
Dotted line here. Then we see that the wind material starts to is in the interior, really innermost part. Then the F value transition down very low value hours.
Dotted, yeah. Okay. I'm with you.
Yeah.
Pretty fine at the scale, but yeah.
Yeah, it's very fine scale here. So here is also the case, and we see then that let me use this case as example. So we see this trace is kind of where we start to have more start to get a little bit out material entering from outer port, and then so the transition finishes at the outer boundary of the molecular outer shell. But here is a little bit tricky. We still have a little bit ongoing transition in between, although the wind material here is very low. It's predominantly ambient material right here. Okay, so that's the structure at the 1,000 AU level. So we notice that those complex internal structures are all slowly or like vortices, but here is mostly can be seen more clearly as vortices.
Yep.
So let me go one. Okay, so this the scale in the context of multi cavities. Then the multi cavities actually can be further characterized in terms of shell structure within bubbles. So the bubble story is that for 1D windblown bubbles, we do form layer structures. So there's the interior transition of wind shock and contact discontinuity and ambient shock. So that kind of structure is actually shown here, but this scale may be very the transition is not clear in college right now, but then it's traced by, in this cases, it's traced by F roughly, but not so clearly in the outer case because there's a transition here. It's the wind shock cavity that's very close, and you can see a little trace here.
Yeah.
You can see the traces right here. So in that language, in that terminology, so in this case, we can say we are seeing a transition from a cavity that where we have primary wind going on unaltered, then it goes through a wind shock. And we are seeing this rolling part as mostly the compressed wind region. And transition hours, we are seeing also compressed ambient region. But here they are kind of mixed together by instabilities. So we'll show that more information in next figure.
Okay.
So this figure is a summary about the structure change in relationship to the colors. So we see how the changes wind fraction from 1 to 0, but we see an in red to blue. So from top down, we can see the wind part is directly going from red, going down from a clear wind shock right here. So they are traced on the upper bounds where the winds are, and after the wind make a jump. Yeah.
Yeah.
This is the outer contour is where they make a jump.
Okay.
This color gives this figure gives just reveals everything. Okay, so we were so surprised when we first saw this first plot because they just summarize everything that's hidden in various scales. So tiny scale, large scale, but when we plot this boom, they all show up. So this is the reddish part is mostly the wind part. And as soon as it actually jump, make the wind shock jump, it start to have tiny mixing, but then still predominantly red. And you see the bottom part. The bottom part is pretty much the ambient shock. The rest of transition is happening vertically in between per theta angle.
Okay.
So basically, this is a figure that we cannot hide anything. So there's a transition from the mostly wind material, and then it's and then predominantly mixing region in between. So it's going down this way. Doesn't matter the lobe is wide or the lobe is elongated. And here, but you can tell, but one can tell between the magnetized case and non-magnetized ambient. Then there's a little buffer. There's a little buffering region in between that's not present in here.
Yeah. Okay.
Okay, so here, so for the hydro case, it's most clear. Now this wind shock, this is ambient shock. It's just up top and bottom. That's the decision. The division is very clear. Whereas the magnetized wind, the wind shock has a jump in between, and it's different MHD shock.
Axis. Very nice. Cool.
Let's go down. So I don't know when we can finish, but so let's go next figure. So the words are then what's the pattern? So if we plot this whole the density structure, those world we found, but if we plot them in the F domain in the fraction, wind fraction domain. And we can see a transition between color from yellow to blue, and the mixture. Although there's a light blue portion here, also surrounding the light blue portion, but we can see there's a pattern transitioning between yellow and blue.
Mixing.
And the pattern seems to be different in that in each case. So we see that from here to here, we see a little bit of structure here, but these two seem to be clean, but here seem to be slightly developing, kind of trying to turn around between the wind and field boundary. So on this column, one can see more clearly kind of this kind of structure to develop around this boundary. And so here we see in the middle part, we see a little bit kind of small structures and going with mixing structures.
Yep.
And here it's more pronounced, but here is kind of shaded by yellow. May not be so clear on screen, but here you can see they are intruding fingers. So the patterns are really different. And here you can see on the rightmost part, when it's not magnetized, the structure going outwards may be more clear. So we can see it's true. It's pointing outwards as well.
Yeah, let's just roll up.
Okay. So we see a variation patterns going in the mixing fraction. Okay, let's go down.
Basically. Okay.
So here we summarize the structure of my outflows, and then we can have outflows that's actually given this different shape, and then this is a figure summarizing the property of outflow in a self-similar manner. So if we kind of scale back all the velocity tracing their respective time frame, they actually can converge back to roughly the same shape, and even given the
2000, 1000, 2000, 1500. Okay. Just getting the colors straight here because you got several colors going on here.
Yeah, so I don't know. And then on the left side, I think left side is 50 kilometer per second, and right hand side is the 100 kilometer per second wind. So between the left and right, you see that well, it's not one outflow, but we kind of scale back to different frames with respect to their different velocity slots on the left and right. So one can see the changes variation of the, but they roughly for per velocity, they are pretty much similar. And per theta angle, their velocities seem to be relatively constant. So that's amazing finding. They follow self-similarity.
Right.
Okay, let's move on to the next figure. So we spent a lot of time at the beginning, but then that's probably have to go through the results of that. So this talk about the self-similarity. And here is the pressure, but pressure meaning we actually trying to compare the pressure. So the left portion is magnetic pressure related properties. The right portion is the pressure related, that's the sum of room pressure and gas pressure. So what we were trying to outline here is that some structures are actually even better seen in pressure space than in density. So we can see those structures actually strengthen as pressure quantities and going inside and outside. So, but it's clear that for at least for magnetic pressure pore, we can see the pressure seems to be in its balance in its own way. Yeah, so that's for more magnetized case. For the right hand side, you see the red part, the inner part is mostly done by wind ram pressure and outwards, and the transition.
Makes a transition over to a beta dominated.
Yeah, so but here you can see the structure is more clearly seen. If in a case that when the ambient pressure, magnetic pressure is slightly weakened, but then you see the different structures shown in magnetic when they're connecting their origin of the structure to magnetic pressure. Yeah, so this so that on the left hand side is kind of buried inside the color. So here you can see more clearly because they are different voids, and then you see them more related to magnetic pressure in the sense. Okay, so let's move on to next figure.
Okay.
And here using this is the same 1000 AU scale, but here we are trying to illustrate the structures we mentioned in density, but here amazingly we show them dramatically clear in pressure. So so here we see the pressure, the cavity. The cavity here, the windshield cavity in magnetic pressure, and then we see that we see different structures develop around across the transition between wind ambient, and we see the swirl here in between so you can see clearly it's a swirl, it's a vortex.
Yep.
But clearly along here. So it's shown much more clearly somehow in pressure figures than in density figures. And then that's related to their magnetosonic origin.
Okay.
So and the multi-arcs, you can see multi-arcs here. So it's even as advertised, it's much more clearly seen in the multi-arc region. So that's the pressure plot, and yeah, so that's, then we label different places where magnetic pressure is balanced by, it's equal to
pressure. Right, those are the contours. Yeah, dotted.
Okay, so let's move on to next figure. So this is a part, and this figure is actually very complex.
I'll say. Oh boy, okay, I gotta blow this down. Okay, hold on. Go ahead, you can chat about it as I get my sizing correct here.
Okay, thank you. So here is actually, this is actually kind of summary plot summary, what we advertise about the C function, the current function, and the force, in how they are describing the molecule in the transition of wind properties into ambient properties. So on the top row for each of those panels, this is already a reduced number of plots from other plots, just to show the relative variation from strongly magnetized wind case to non-magnetized case.
Yeah. Right. Each of the three, and I'm going to blow up on one just to get my axes straight here. Hang on. Okay, I can't.
To really weakly magnetized case, so we can still calculate the magnetic forces. So here, so in those plots, the topmost panel plots the left one as a density, the right one as a C function. So that's the C function we advertise. So
okay.
So the C function, so what we thought is a core expression of the whole property. So they seem to be clearly described as a gradient of property. That's wonderful. So they are making clear transition from the inner part that when the wind is unheated, into the ambient material and ambient part where it's holding a constant value. And then so the middle part is the magnetic forces in the middle part.
Okay.
And the bottom row of each panel shows the velocity component. The right part is the radial component of velocity, and the left part is a theta component velocity.
Okay.
So all the doubles are summarizing this plot in some sense, in that we show the connection between the structures formed within the molecular outflow and in density in C values, and in a radial component of forces, that's this one, and in theta component forces, and we see how the structures are connected from one to the other. So that means the structures are also they are related to magnetic forces, and therefore the velocity are also responsive to the change with respect that's coming from the forces. So we show the structures are really intimately connected in all these quantities. So here we show their patterns, and their patterns are actually shown in the velocity patterns and in the force patterns. So each part of the force panel, we see oscillating components. The components are oscillating in that they may change signs, or they may and to give a structure. For example, use this as a case. And then theta value of the velocity is also showing its with respect to its change of magnitude and change of directions. Whereas the VR is more monotonic, but in detail there are still oscillations, but overall going outwards, they seem over more or less of drop from inner portion and to the second portion to outer portion. So they seem to give a different drop according when they cross the shop. So, but then they seem to be more, but then if we plot on this scale, they appear to be going outwards, kind of decreasing outwards. That's what they appear. So you can see from the velocity to be yellow to red. And so I really, so we have, so we can show that there are so many very fine structures in the forces. So therefore, they are actually, we can trace how the force can really connect to each other. So that's the origin of the part of origins, we can say at least, of the structure formation is related to magnetic forces.
Yes.
Summarized to this page into the most superficial way.
That is a wild plot. That is a wild figure.
Oh, right. But then, yes, but it tells us so much that they are corresponding to each other. So, but then see, then relatively, we see when the magnetic forces are very much weaker and things are dying down, and then we don't see any, we don't see structures formation within the lobe, and that's what we go down. Okay, so we can go down to the next figure.
Morphologies.
Yeah, we go back to morphology. Here is what we go back to how we kind of approximate the field, the morphological structure in terms of momentum conserving shells for the hydrodynamic case, and how we approximate the relative contribution to to ambient pressure. So ambient magnetic field pressure, so we can trace all the shells and in their respective locations. So we can see, and the dashed lines are the fits. So and the other contours are their original scaled shapes. So we can see that the fits pretty much are well for the interior part. For the outer part, we can fit this part. And for this non-magnetized ambient medium, so we can see if we include the magnetic toroidal pressure inside, we can roughly recover the shape. So this is an improvement over hydrodynamic consideration, that to consider the pressure contribution into the equations. So that's kind of semi empirical fits to the results, and it's an introduction of a shape and its relevance of relevant importance of pressure, RAM pressure to ambient pressure.
Correct. Yep.
Okay. So then next section 7 is the new part of Kelvin-Helmholtz instability. Are you sure? Should we go on?
No, we're good. So this is
okay. So this section 7 is about Kelvin-Helmholtz instability. So we discover in this system that there's the slope shear and the origin, and this shear is actually can generate Kelvin-Helmholtz instability. And they are actually generated between the reverse shocks and ambient, wind shock and wind shock and ambient shock in the hydrodynamic sense. So in the magnetized case, so they are actually produced also in the reverse shock and outermost ambient shock. So then we see this part is to capture the situation and level of vorticity. Well, and vorticity created in this area in between this region. So we plot vorticity, total vorticity capture in this region in between this. So we can see the trace. So this color completely delineate the boundaries between the white part inside is really the free wind. So it's labeling the free wind region very clearly, because the free wind is completely vorticity free.
Right.
And when the vorticity will only be generated once it crosses this boundary, the first reverse shock boundary, and it's most dramatic between the interface. So some cases you can see the interface is clearly traced by the color between the kind of wind wind field boundary and outer field boundary. So that this is in vorticity space. So same thing, and then you see the kind of multi-arcs much clearer here, but the wind compressed wind part is inside. This inner part is compressed wind. And here we can see the region kind of narrows down when the wind is not magnetized. We see we recover to the thin shell models when both sides are hydrodynamic. And the inner part, then this figure pretty much summarized the sizes of so-called mixing region that will have theorized between a shear to a shear region. So one used to think that the mixing region for molecular outflows may be thin. Then that yes, we demonstrate it's thin, but for magnetized case, when wind is magnetized, the mixing region is very thick. It's pretty much occupying a lot of space.
Yep.
So.
Indeed, way bigger. Okay.
Yeah. So the text part is okay. So I'm skipping detail of the text here because we went into the reason why we think it's a Kelvin-Helmholtz instability, and we show that vorticity can be generated by magnetic forces. And indeed, we can compare. So that's why the vorticity plot shows the differences between magnetized case and non-magnetized cases. And in this figure, we actually kind of summarize the stability criteria for Kelvin-Helmholtz instability. In that, by what we knew at that time, when we finished the manuscript, we can capture what we understood. We are testing what our numerical results will be if we were to test with the so-called stability criteria for Kelvin-Helmholtz instability. In that, most of the cases are magnetized, and only one case is purely hydrodynamic, but with hydrodynamic division between hydrodynamic wind and magnetized medium. So we are covering also a huge space in terms of study of Kelvin-Helmholtz instability. And what's special about this our configuration is that we have a toroidal field inside and we have colloidal field inside. This kind of configuration, at least we didn't find easy literature for the study. Okay. So therefore, that presented a challenge for us to understand the structure. So fortunately, it looks like the toroidal field present a give us a tremendous advantage, because this toroidal field inside, they actually kind of actually delineate a very good boundary between the wind and the ambient field. So the boundary between where the toroidal field covers is actually a natural contact discontinuity or initial contact, but layer is
clean. It's very clean.
Yeah.
Clean.
What should I say?
Yeah.
I totally forgot one thing. So
this is radial and this is theta on the bottom, right?
Yeah. So it becomes what should I say?
I mean, they're Mach numbers.
Yeah. So they actually. So yeah. So they actually can separate. So that becomes the most clear place where we see the most shear may happen. Although the shear so where we can easily imagine where the inner outflow can have a shear relative to the outer boundary. But then and that's where the instability of we think as Kelvin-Helmholtz origin can be generated. So they all come from this boundary. Either they can have a swirl shape or anything. So that depends on detail modes of Kelvin-Helmholtz instability. We didn't go into detail about.
Yes.
And so we can see, so why we are doing that? Because we were trying to, we were trying to use the velocity, convenient velocity decomposition for our radial velocity component and V theta component to see which one actually plays a role to be the transverse component parallel to the shocks or vertically normal to the shocks, but it's not so obvious. So then to capture the overview view, so we do this 2-panel. On top is the radial component. The bottom one is the V theta component. So one can get a glance. So without bias, that we show people clearly how the transition happens with respect to magnetosonic Mach numbers and interior to the wind. For outer part, when it's magnetized, we use also magnetosonic Mach numbers, but we use a poloidal field for the magnetic field strength. But when it's not magnetized, we use sonic. We use just sonic Mach number for labeling the transition. So we can see by colors and how these numbers change. And we see that everything changes again in the region, in between the two shock region. And their respect number. So to summarize in a few sentences, the toroidal field cannot stop the Kelvin-Helmholtz from really going into the wind, because it's a transverse field component. So the Kelvin-Helmholtz in this configuration instability actually Kelvin-Helmholtz instability actually behaves as the regular hydrodynamic Kelvin-Helmholtz instability, where it actually goes unstable for virtually any Mach number. For the poloidal component, we actually can find that there is a kind of criteria about Alfing Mach number 2 around that. So where kind of separates super sonic super magnetosonic instability or not. So that's what this figure is kind of supporting, being that in the outer part, we see that when the colors are going beyond the number 2, we see more rugged surface, whereas we see no Mach number that can stabilize the interior. Even though apparently some figure may apparently by color it looks very smooth, it's because of color, the limitation color. But then in detail they are small. They are just a side in terms of difference, whether they go extremely nonlinear or not. So that's this figure kind of summarize that nature and the criteria, and then rough stability criteria for Kelvin-Helmholtz instability under influence of toroidal magnetic field and poloidal magnetic field in ambient medium.
Very nice.
So, and figure 7 is a summary of what we found. So this paper, what's telling us the size of the detailed structure of molecular outflow from inside out. So we found that because of our radial wind, and And after we study the forces, we feel that the v theta could be the theta component velocity could be a good indicator of the transition into different regions. They actually tells different things when they go into from the free wind region and compressed wind region and compressed wind region and fully ambient region. So then we show the correlation with the wind mass fraction on the left lobe and the theta component on the right.
For example, here. Yep.
Yeah, so you can see good size, and the sizes are there,
right.
And where they're located, and where the kind of they are thick, they are going there, they are fingers. So you see how they are really correlated, and how where they are distributed from bottom to top. And we know that, so it goes all the way up, and then you see the patterns are distributing around it. So one note is that when one look at those structures, because the structures are actually very fascinating in that when they can create all kinds of visual impressions when we look at the nonlinear structure on instability. So this figure by itself details the relative size at different locations where they are distributed, how deep they are going into, but also they tells us the patterns of theta component velocity, how regularly varying it is response to the transition. So okay, so that's it's a very thick. So for magnetized outflows, it's a thick mixing layer or thick mixing region. And what's telling us in this figure here is we did a kind of column density integration. So if you don't mind, could you enlarge it? So so we were trying to demonstrate that the complex internal structure developed by this nonlinear Kelvin-Helmholtz instability. Nonlinear growth of Kelvin-Helmholtz instability can create many different interpretations of structures when one look at the images or lines. So here, without doing other radius transfer, we simply integrate the column density. So between left and right, we can see, so we show in the intermediate case, so we chose this from the pattern when, for example, from the MA equals 30. So this,
right. Okay.
Yeah, can we go one more up? Yeah, so go back. Yeah, so for example, this MA equal to 30. So the pattern for MA equals 30, we can see is more tightly packed threads. So in this sense, so we are seeing that it's a kind of narrow cavity inside, and we are seeing a packed structure outside, and we see a few darker path going through. So if we do look at them on the right-hand side, we see a darkened shell-like structure, indicative of, sometimes we can consider them like injections of different epoch of injections. So here you can see it's more dramatic in this case. So we can see the swirls all lined up all the way up, and on the right-hand side, they appear of multiple injections. Yes. Just a series of knots going up. So inside of a kind of cocoon around here, and that's the visual impression that one can interpret as they are actually different injection. So this is a series small injection, small injections, and those can be interpreted large injections. So, and then we can go down next, point one, when ambient field is weak, is even pronounced. So we can see various structures, and then we can interpret, they can look like they are layers, they are multiple shell structures from inside out, like that.
Mhm.
So here is also giving you the nested sense, giving you the side sense of nested shells.
Yeah, a little more tangled here too as well.
Yeah. So this then for next one, then we see for non-magnetized medium, we see the interior one. What we don't see more outside. So that can give you observational differences.
Mhm.
So this is summarize the main part. The rest is appendix. Then we show a little bit details of flow structures, documenting our the theoretical concept we are using in terms of bubble theory. So, well, yeah, I'm jumping to the appendix already, but then we have a huge section about observational implications, where I kind of summarize in the figure that we talk about different visual impressions those structures can make, and how when one look at the whole outflow, we have many different interpretations thinking they may be injection, but when we don't have a real multiple injections for those, so nonlinear structures can magically create that impression. And in many sources, a few sources we can that came to our to
Okay.
find in attention. Okay, so this is summary of the paper. So the first few points, we kind of summarize the large jet shell structures of varying degrees of collimation, actually natural products models of dual characteristics, meaning they can have a deeply densely jet and wide angle wind. And those characteristics
Mhm.
is really a MHD product. And then so the collimation of jet is by magnetic forces, while the collimation of lobe is pretty much interaction, a product interaction between the wind and the surrounding ambient
Yep,
medium.
that came clear. Mhm.
So,
Cool.
and that's number 3. And number 4 is the shape outflows reflects the bouncer run pressure and ambient magnetic pressure. And aspect ratio is generally determined by flattening of toroid density, wind strength, and ambient pressure. So the overall, the evolution is subsimilar.
Mhm.
And let's see, 5 opening angle is also vary with evolutionary stages. So in terms of n value, it's simply labeling the evolution, the expected evolution, the direction of evolution is to open up the toroid going from narrow to wide. So that's a natural direction.
Yep.
And we expect that to be subsimilar, and that have been shown in the past to be that way. But further detail can be worked out in future models. And so number 6 was basically summarizing a layer structure, and number 7 is the multi-cavity natures, then how they are nested together from inside out. And number 8 is is a generation of wide angle ring with a predominantly toroidal magnetic field. How the generation of bipolar generation of Kelvin-Helmholtz sensibility can be present and go nonlinear in this kind of wind and in this compressed wind portion. And so it's the Kelvin-Helmholtz instability are tracing the pole shock region and and the vorticity can be also further generated, or one way or the other, by magnetic forces in this compressed region.
Okay.
So enhanced. So, and then see, yeah, so we talk about the Kelvin Helmholtz, maybe really this dominating agent playing the structure formation between this between the wind sharp ambient region. And then they are natural oscillation, either due to the force generation or due to the interaction, nonlinear generation of the modes. So all this part can be further studied. So number 12 is we are our results, because given the wide coverage of our parameter space, so we actually accidentally sampled a wide space of generation of Kelvin Helmholtz sensibility under different configuration that's rarely studied. So this is well, that gave us a lot of the incentive for studying further Kelvin Helmholtz sensibility, for example. So
Awesome.
Okay, so that's the end of major paper. The appendix is pretty much document material supporting the reason we did our analysis in the results section, and in the force in the Kelvin Helmholtz section. So we did work out an example. We do a few slices of velocity structure in the hydroshell, so one can see clearly the shear pattern is established. So that's a summary, a short summary. What we did in I think we have 4 appendixes. So thank you.
Well, as extensive as that survey was, I'm sure there are things in the future that need to be done. Are there new observations coming that you may be able to verify, validate, validate's the better word, the calculations, or are there new sets of calculations that going on? For example, 3D, or relaxing the isothermal assumption, or what's next? Where do we go from here, given what you published?
Where are we going from here? There are so many. Okay, so yeah, so next thing, well, we definitely, well, of course, use validation. So we want to develop a few things that will help people observers develop observational strategies to detect the features where things are at. So then we also like to put things, the missing ingredients. For example, in future we may study collapse in interacting with a collapsing medium, or as you said, maybe we may, that's of course, we may consider relaxing the isothermal assumptions. So those are natural follow-ups. So in a slightly moving forward, we want to understand the modes, and we want to understand how it's really connected to the inside out in a more complete picture.
Okay.
Or going outwards inside. So that's
work. Very nice.
Thank you very much for this discussion. I'm sorry it takes a long time.
It is. It was great. It was fantastic. I want to thank you so much, Sienna, for walking us through your very lovely paper. It's awesome.
Okay, thanks a lot.
All right, everyone. Thank you so much, and we will see you on the next one. Bye-bye.